Hello everyone. We'll be continuing on Cartesian particle kinematics, and we'll be looking at a case of a curvilinear motion of a projectile under constant acceleration. Okay, so let me start off by saying, so consider a projectile which is traveling with an initial velocity of V naught, making an angle of theta naught with the horizontal. Okay, I'll show you that. Okay, and under constant acceleration due to gravity. Okay, projectile is any body that is projected into space with an initial velocity. Okay, so projectile is any body projected onto space with an initial velocity. All right. And in this problem, we will be neglecting the effects of drag forces. Okay, so we will be neglecting drag for the time being. Okay, all right. So let me start off by drawing Cartesian coordinate frame and then looking at the hypothetical motion of this projectile. So Cartesian coordinate frame, as you know, is your typical x-axis and y-axis as drawn here. Okay, so this is the x direction, this is the y direction. I have some unit vectors along these directions which I typically mark as I and j, so I'm just going to mark that here. Okay, so this is I and then this is j. For the trajectory, I already have the trajectory drawn, so I'm just going to pull that up. Okay, so I'm assuming that this is some hypothetical trajectory for the particle. Okay, then what I'm also told further is that, okay, hey, this particle has some kind of an initial velocity. Okay, so I'm going to draw the initial velocity vector. So at this particular point, it is tangent to the path of the particle. Okay, so I'm just going to make this tangent to the path of the particle. So slightly here, okay, at the starting point itself. Okay, and I'm going to call this velocity vector as V naught, and it's making an angle of theta naught. It's a pretty sharp angle here. Okay, it's making an angle of theta naught with respect to the horizontal x-axis. Okay, so we are given V naught and theta naught, and all of this motion is observed by this stationary observer at this point. Okay, so the stationary observer is the point O. Now at any point on the trajectory of the particle, if I draw the velocity vector, right, so for example, if I draw velocity vector here, that's going to be tangent to the path of the particle. Okay, if I draw the velocity vector at this point, that's also going to be tangent to the path of the particle at that point. So this is going to be v at some point in time, this is v at some other point in time. At any point, I can look at the x and the y components of v. Okay, this you know from basic Cartesian coordinate frames. I'm going to have a y component and I'm going to have an x component. So this is vx, this is vy. Okay, and likewise I'm going to have an x component here that is pointing in the horizontal direction. I just want to get these guys to snap together, but I guess they're being a little difficult today. Okay, and then likewise I'm also going to have the y component that is drawn starting from here. Okay, so that's the y component and the x component at that point on the trajectory. And you can look at the acceleration vector at any point. The acceleration due to gravity is going to be pointing down because of the way we are looking at the problem. Okay, which means that at any point in the trajectory, what's the direction of the acceleration? It's going to be vertically down. So this is A. Okay. Then at some other point in time, this is also the acceleration vector at that point in time. So this is also A of t. Okay, or I can write this as a vector quantity if necessary. So I'll just leave it in this form since I already have the direction written. Okay, this is A of t here, and so on. Now this V naught, if I look at V naught, right, I can break it up into its components along x and y directions. Okay, so the first thing I'm going to do is break V naught into components along the x and the y. Okay, so for that I have the following figure, right? Essentially I'm taking V naught. Okay, so this is V naught, and then breaking it up into a component along the x direction and the y direction. Okay, if I draw the right angle triangle, of course that's going to be the situation. Okay, so this is theta naught is the angle here. This is going to be Vx naught, Vy naught. So this guy here is also going to be Vy naught, right angle triangle, as you know, which means that Vx naught is V naught cos theta naught, and Vy naught is V naught sine theta naught. And we are given V naught and theta naught. Okay, so note that we are given V naught and theta naught. Okay, and these are the components of the initial velocity along the x and the y directions. All right, how do I start this problem? Okay, this hypothetical problem is, my aim here is to look at some relationships that arise from this particular problem. So I'm going to start with the acceleration vector first of all. Okay, so we know acceleration at any point of the trajectory is always pointing vertically down. Okay, which means that if I write the acceleration vector, it is not going to have a component in the x direction at all, and it's going to have a component in the y direction which is going to be pointing vertically down, which means if I compare this with the expression axi ayj, it is quite obvious to see that, okay, by comparison I'm going to have ax is equal to 0 and ay is equal to minus g. Okay, but then from Cartesian coordinate frame we know the following. Okay, we know ax is equal to dvx by dt. Okay, this is from Cartesian kinematics. Okay, which tells me that, okay, hey, if I now do the substitutions, I'm going to have, but for us ax is equal to 0, which implies that dv by dx dt in the x direction is going to be 0, which means that if I do the integration of dvx, this is going to be integral 0 dt. I'm going to start with some initial velocity, go to some velocity in the x direction. I'm starting with some initial time t naught, and at some point in time t, it's quite obvious that integral of 0 is going to be 0, and so I'm going to end up having Vx is equal to Vx naught, which is V naught cos theta naught. Okay, so this is going to be the case at any point on the trajectory. The velocity in the x direction is always the same. Okay, that's the consequence of this particular equation. Okay, so what this tells us is the following. At any point on the path of the particle, the x component of velocity is a constant. Okay, it does not change with time. Then what about the y component? So we know ay is dvy by dt. Right? This is also from Cartesian kinematics. Which means that for us, though, ay is equal to minus g, right? This is what we had from there. Okay, maybe I want to put a line on these two as well. Okay, so these are also crucial pieces of information. Okay, so ay is equal to minus g, which tells me that dvy by dt is equal to minus g, which means that I can cross multiply and say, okay, dvy is minus g times dt. Integrate this from some initial value vy naught to some value at some point in time, and integrate this from some t naught to some point in time t. Okay, after I perform the integration, I'm going to end up having the following. Okay, so vy is going to be vy naught minus g times t minus t naught, or substitute for vy naught. Vy is v naught sine theta naught minus g times t minus t naught. Okay, so this is typically what I ended up with in the y direction, and you obviously see that the y component of the velocity is not necessarily the same at all points. It's going to be changing with time. Okay, so that's also something you want to note. Okay, so the y component of velocity will change with time. Okay, so I have the x and the y components. Let me go ahead and find out how the displacements might look like. Okay, so here is what I'm going to do. Okay, so my next point. So we know that Vx is equal to d rx by dt, and I'm just going to call this as some dx by dt. Okay, so say that rx is equal to x of t. Okay, does not make a difference to me. Okay, and what is Vx though? Vx from before is just a constant V naught cos theta naught, right? So I'm just going to plug that back in here. So which tells me that V naught cos theta naught is equal to dx by dt. Okay, which means that if I cross multiply, I get the following. Okay, so dx is V naught cos theta naught dt, integrated from some initial value to some value in time t. That's the position. Okay, and if I do the integration, I end up getting the following. Okay, so x is equal to x naught plus V naught cos theta naught times t minus t naught. Okay, this is fairly straightforward integration, so I'm not going to go over the details of these things. Copy that, and I'm going to put a box around that, and once you put a box around these things, you can forget them. Okay, then we also know that Vy is dry by dt from Cartesian kinematics. I'm going to write this as dy by dt by saying that Ry is equal to some y of t. Okay, why not, right? Which means that I have an expression for Vy, which is this big guy here, V naught sine theta naught minus g times t minus t naught. Okay, so I'm going to substitute that. So this is V naught sine theta naught minus g times t minus t naught. This is equal to dy by dt. Cross multiply and integrate. Okay, so this tells me that okay, dy is equal to V naught sine theta naught gt minus t naught, all of this times dt. Integrate this from some initial height to some height y. Integrate this from some initial time to some time t. I'm once again going to skip the details of the integration. Okay, so this will tell me that okay, y is equal to y naught plus v naught sine theta naught times t minus t naught minus g by 2 times t minus t naught whole square. Okay, this is the expression. It's a fairly common expression that you would have seen in the case of a constant acceleration case. Something happened here which may be a kink in space-time, probably. I had a black color there. Okay, then what am I going to do with all these? Of course, I can solve problems with all this information, but you got to be careful. Whenever you solve problems, you got to make sure that okay, hey, is the acceleration in the vertical direction? If you're looking at projectile motion, if it is not in the vertical direction, right, then you may have to take the component of acceleration in the x and the y directions. Okay, now very quickly, I want to do something called as the time of flight. Okay, so time of flight and the range of projectile. Okay, time of flight I'm going to call that as TF. Okay, this is the total time taken for the projectile to go from the launching point to the point that it impacts the ground. Okay, so this is the total time taken by the projectile to go from launching point to point of impact on the ground. Okay, that's something that you want to make a note of. And the very last thing that I want to talk about is the range of the projectile. Okay, so range of the projectile. Okay, this is the maximum distance traveled horizontally by the projectile. Okay, from start to stop. Okay, maximum distance traveled, maximum horizontal distance traveled by the projectile. Alright, in many problems that I'm going to be solving on projectile motion, I will look at the time of flight and I will look at the range of the projectile, and we'll use that for that particular situation. Alright, thank you very much for your patience. I'll see you in the next concept talk. Bye-bye.